Every single day, the United States alone extracts over 9 million barrels of oil. A single barrel holds nearly 159 liters. Now multiply that by thousands of wells across the planet. But have you ever stopped to consider what oil actually is and how it is formed? This isn't just a black liquid. It is the result of immense geological forces acting over millions of years deep within the earth. Oil is born from the remains of ancient life, transformed by pressure and heat into a liquid hydrocarbon. And from there, the modern story begins. A high-stakes hunt, deep earth drilling, and the incredible process that turns this primordial substance into the fuel that moves our world. It's expected that the average daily oil output in the U.S. will soon reach 9.9 million barrels. But what exactly is this substance we call oil? The process of its formation is a slow, powerful saga that unfolds over geological time. It begins with the accumulation of organic material, the remains of ancient plants and animals at the bottom of seas and lakes. Over millions of years, these remains are buried under layers of sediment. Under the immense pressure and heat, this organic matter transforms into a waxy substance called kerogen. Further heating, in a temperature window between 60 and 150 degrees Celsius, triggers the thermal breakdown of kerogen, creating liquid hydrocarbons. And that is what oil is, the distilled essence of ancient life. Once formed, this oil migrates through porous rock until it reaches a geological trap, a structure that blocks its path. Here, it accumulates, forming a reservoir. To find these hidden reservoirs, we must first understand the earth beneath our feet. This is the world of geological surveying, one of the most complex and expensive stages of the process. Scientists use satellite imagery, magnetometers, and seismic waves. Seismic surveying is particularly spectacular. Controlled underground explosions are triggered to send shock waves deep into the earth. By reading the echoes, geologists can map the subterranean landscape and identify potential traps. When a promising zone is identified, the drilling begins. A land or offshore rig becomes a giant mechanical creature operating day and night without pause. The drill string, steel pipes with a cutting bit at the end, bites into the earth, rotating at up to 200 revolutions per minute. A special drilling fluid is pumped down to lubricate the bit and carry rock cuttings back to the surface. A modern well can reach depths of 3 to 5 kilometers, and in some cases 10 or even 12. In Texas or Saudi Arabia, wells are drilled over 8 kilometers long, often with a significant horizontal section to maximize contact with the reservoir. A single drilling operation can cost tens of millions of dollars with no guarantee of success. But when a well strikes oil, it begins its journey to the surface, either under its own pressure or with the help of powerful pumps. Saudi Arabia is one of the world's oil titans. In February, the kingdom was producing nearly 9 million barrels per day, and its position is only set to strengthen, as Saudi Aramco has recently discovered 14 new oil and gas fields. Once the well is completed, the extraction phase begins. In a rich reservoir, the natural pressure is enough to force the oil to the surface. This is known as a gusher, and while it looks impressive, it's now considered an outdated and dangerous method. Modern wells are fitted with complex valve systems, known as Christmas trees, that allow for precise control of the flow. The crude oil emerges and is sent to a processing facility where it is separated from natural gas, water, sand, and other impurities. This often happens right at the well site. The separation is a fascinating process. The mixture enters a large sealed vessel where gravity takes over. The lighter gas rises to the top while heavy water and sediment sink to the bottom. Sometimes, water is trapped in the oil as a microscopic emulsion, which is harder to separate. In this case, chemical de-emulsifiers are added to break it down. To maintain pressure in an aging reservoir, secondary recovery methods are used. Water or gas is injected into the formation through other wells to push the remaining oil towards the production well. These techniques can allow up to 60% of a reservoir's oil to be recovered. The average modern well in the U.S. produces between 500 and 1,500 barrels per day. A single barrel is 159 liters. Multiply that across thousands of wells and you begin to grasp the true scale of this global operation. Crude oil itself is a complex cocktail of hundreds of different hydrocarbons. To turn it into petrol, it must undergo a series of technically demanding stages at a refinery. It all starts with fractional distillation. The crude oil is heated to between 350 and 400 degrees Celsius and fed into a tall distillation column. The various components of the oil vaporize and rise to different heights inside the column before they cool, condense, and are drawn off. The petrol fraction is one of the lightest, and it's typically collected at a temperature between 40 and 200 degrees. But this initial distillation only yields about 15 to 20% petrol. To increase the yield, a process called cracking is used. This breaks down long, heavy hydrocarbon molecules into shorter, more valuable ones. The most common method is fluid catalytic cracking, where heavy fractions are heated to nearly 1,000 degrees in the presence of a catalyst. This allows for a much higher yield of petrol from the heavier residues. Hydrocracking, which uses hydrogen under high pressure, is also used. Ultimately, the petrol yield from a single ton of crude oil can be pushed as high as 40 or 50%. The petrol produced so far, however, has a low octane rating. To fix this, it undergoes reforming, a process that restructures the molecules at high temperatures using a platinum catalyst. In the final stage, additives are blended into the petrol to improve its properties: anti-corrosion agents, anti-knock compounds, and detergents. This ensures engine longevity, reduces harmful emissions, and improves efficiency. A single modern refinery can process up to 400,000 barrels of crude oil every single day. The sheer volume is staggering, especially when you consider that the daily petrol consumption in the U.S. alone is around 1.4 billion liters. A river of ancient life, powering the modern world. Every year in Dubai alone, over 1 million tons of asphalt are produced, and that number is constantly rising. Imagine it, tankers carrying millions of barrels of crude oil dock at Jebel Ali port. The oil is distilled in reactors at over 350 degrees Celsius, and a black, heavy residue is transformed into an advanced, elastic bitumen. Then come minerals from the mountains of Fujairah, processed at hundreds of tons per hour, blended in automated mixers, and transported in insulated trucks. This is the engineering magic that gives Dubai roads that neither melt in the sun nor crack in the night. Watch until the end, and you will discover the secret that makes this asphalt tougher than the desert itself. It all begins on the waters of the Persian Gulf, where giant tankers slowly cut through the surface, carrying millions of barrels of black gold, crude oil. They journey from Iraq, Saudi Arabia, and Kuwait. When a tanker docks at a port in the UAE, such as Jebel Ali, a process begins where men and machines work as a single organism. The oil is pumped into vast storage tanks, hidden within the industrial landscape, marking the start of its transformation. From there, it travels underground through a network of pipelines, like arteries leading to the heart of the refineries. In Jebel Ali or Abu Dhabi, it is met by a city of steel, reactors, distillation towers, and chrome columns. Here, the crude oil is heated to over 350 degrees Celsius to separate it into fractions. Lighter components, petrol, diesel, kerosene, vaporize first. The heaviest residues, the ones that refuse to vaporize even at these temperatures, are exactly what we need. This residue is fed into a vacuum distillation column, where the pressure is dropped to a minimum. What remains is bitumen, a black, viscous substance, the soul of asphalt. On its own, however, this bitumen is too thick and brittle for road construction, especially in a desert where the surface temperature can reach almost 50 degrees. So it must be modified. In special reactors, the bitumen is blended with polymer additives, plasticizers, stabilizers, and sometimes even crumb rubber. This is the bitumen modification process. The result is a material with high elasticity and resistance to UV radiation, one that won't soften under the sun or crack when the temperature plummets at night. In Dubai, a polymer-modified bitumen that meets the strict standards of the RTA, the Emirates Roads Agency, is used almost exclusively. Once the bitumen has completed its transformation, it begins the next stage of its journey, delivery to the asphalt mixing plants. The modified bitumen is transferred from the reactor into insulated storage tanks which maintain its temperature at around 175 degrees. In this liquid state, it remains perfectly uniform. It is then pumped through high-pressure sealed pipelines to the nearby plant or loaded into road tankers with special thermal containers. These tankers are built with a double-skinned steel body and a thick insulating layer. The drivers undergo special training. They must maintain a steady speed and monitor temperature sensors in real time. If the temperature begins to drop, an onboard heating system activates. At the plant, for example, the DXB Asphalt factory in Dubai Industrial City, the tanker connects to the intake system. At this moment, the bitumen is hot, thick, and has a distinctive smell. It is pumped into the plant's holding tanks, where it waits to be precisely dosed. From this point on, it is no longer just a material. It is a component in a formula, where the weight, viscosity, and temperature of every ingredient will determine the lifespan of the road it is destined to become. One of the largest plants is the DXB Asphalt factory. Here, the bitumen is heated to 160 degrees and mixed with mineral aggregates, gabbro, basalt, and quartz sand. Gabbro is a dark volcanic rock quarried in the mountains of Fujairah. The rock is crushed into fractions smaller than 25 millimeters, screened through vibrating sieves, dried in huge rotating drums, and then fed into the mixer. Inside, the bitumen and aggregates are combined into a hot, uniform mass known as hot mix asphalt. The temperature of the mix is 160 degrees. It must be perfectly homogeneous with a precise ratio of components. After mixing, the asphalt is transferred to insulated silos where it can be stored for no more than 6 hours. From there, it is loaded into insulated trucks for the final journey. On site, the asphalt is laid by paving machines and then compacted by rollers, first vibratory, then static. In the desert, achieving maximum density is critical to prevent the ingress of sand and water. Compaction is done in multiple passes, and the temperature of the asphalt must not drop below 120 degrees Celsius during the process. If it does, the mix loses its workability and the road's integrity is compromised. A key feature of Dubai's highways is their multi-layered structure. The base course is made of a coarse-grain asphalt. The middle, or binder course, uses the modified bitumen and acts as a shock absorber. The top, or wearing course, is a thin layer with a high polymer content to provide grip and durability. In some cases, reflective minerals are added to reduce heat absorption. In the desert, it's not just the heat. Dust, wind, and humidity changes all have an impact. Asphalt plants in Dubai are equipped with advanced air filtration systems, and the mixes themselves are tested for resistance to abrasive wear and thermal expansion. In the RTA's laboratories, every batch of asphalt is checked for viscosity, density, and thermal stability. If it fails to meet the standards, the entire batch is rejected. This journey, from oil tanker to finished highway, takes several days, but involves dozens of quality control stages. And it is because of this meticulous process that Dubai's roads can withstand the daily punishment from thousands of vehicles without melting under the desert sun. Over 1 million tons of asphalt are produced in Dubai annually, and this figure is growing with the city's infrastructure. The DXB asphalt factory alone has a capacity of 240 tons per hour, allowing it to supply major projects without interruption. For comparison, an average plant in Europe produces around 150 tons per hour. Interestingly, asphalt is the most recycled material in the USA, with over 99% of old pavement being reused. Dubai is also actively adopting recycling, especially during the reconstruction of older highways.